There are two forms of a quadratic function that you want to be familiar with. In 3.4.2, they're called the general form and vertex formula. The vertex form of a quadratic function is f of x equals a times x minus h quantity squared plus k. In this particular form, we can recognize the transformations from the parent function x squared. In the previous video, we mentioned that this one is stretched by a factor of a, it is shifted to the right by h units, and it is shifted up by k units. Because we can recognize those transformations, and we know the parabola has moved right, h, and up, k, we can recognize that the vertex is hk, ordered pair hk. Notice there was a change in sign for the h, but there was no change in sign for the k. Again, the reason for that is simply because we're looking at the difference between a horizontal and vertical transformation. If the parabola is presented in vertex form, we can efficiently graph it using transformations. However, if we were to multiply out the x minus h, distribute the a, and combine like terms, we would eventually end up with a parabola that looks something like this. This is called the general form of a quadratic. In this case, we cannot look at it and observe the transformations. So in this case, we will apply a vertex formula. This will remind you a little bit of the quadratic formula. To find the vertex of a quadratic function in this form, we're going to calculate x equals negative b over 2a and y equals f of negative b over 2a. This is a formula that you will want to memorize. We'll be using this often. So again, if we are given the general form of a quadratic function, then the way we locate the coordinates for the vertex is by calculating negative b over 2a. And again, I'm just picking up the coefficients just like I would for the quadratic formula. So the x-coordinate is calculated as negative b over 2a. Now, once I get that number, then I plug that number back into the function, and that's going to yield the corresponding y value. So again, memorize that very important formula. If we have this parabola in the general form, this is our approach to graphing it. Number one, determine if it opens up or down. Remember, if the leading coefficient is positive, the parabola opens up. And if the leading coefficient a is negative, that represents a reflection across the x-axis, our parabola opens down. Now, pay attention to that orientation information because as you'll see from the following examples, sometimes that can save you a little bit of work. Once I know the orientation of the parabola, step 2 is to find the vertex. And in this general form, we're going to use our new formula, negative b over 2a, f of negative b over 2a. Step 3, we will then determine the equation of the axis of symmetry. If you'll remember, the axis of symmetry is this line that divides our parabola into two matching halves. That axis of symmetry always passes through the vertex. If you'll remember, the form for the equation of a vertical line is x equal to a constant. So when we write the equation for the axis of symmetry, it will be x equal to some number. Well, that number is going to be the x-coordinate of our vertex. So we get a lot of information out of negative b over 2a. That's the x-coordinate of the vertex, and that is the actual equation of the vertical line that passes through the vertex. Step 4, we will find the y-intercept in the same way that we always find the y-intercept, and that is setting x equal to 0. What you're going to find in this particular form, notice if I set x equal to 0, that term goes away. This term goes away, and this little fella is the only one that is left. That gives me the y-intercept. So the shortcut to find the y-intercept of a quadratic is just to observe whatever that constant is out there. So we could make ourselves a note on the shortcut. The y-intercept is 0c. Next, find the x-intercepts in the same way that we always find an x-intercept. That is, set the opposite variable y equal to 0. Now, at that point, you will have to depend on your skills to solving a one-variable quadratic equation. You may need to solve by factoring, you may need to solve by quadratic formula, or even the square root property. And then number 6, once I have all that information, the x-intercepts, the y-intercept, the vertex, the axis of symmetry, I'm going to plot all of that on the grid and then connect the dots using that smooth U shape. And then finally, we will observe the domain and range and write those in interval notation. So let's give this new process a try. Example 2, graph each quadratic function following the above steps. Example A, f of x equals x squared minus 2x minus 3. Notice this is in the general form, not the vertex form. So I'm going to begin by recognizing the orientation. That is the direction of opening. Since our leading coefficient here is 1, we're observing that it is positive. Our leading coefficient is positive, therefore our parabola opens up. So we're going to keep that in mind. Once we know the direction of opening, we can then work on finding the vertex. Since this is in that general form, we're going to use our vertex formula, negative b over 2a, f of negative b over 2a. So there are two coordinates to the vertex, an x-coordinate and a y-coordinate, and we're going to find them one at a time. We will start with the x-coordinate. The x-coordinate is calculated as negative b over 2a. Looking at our original function, b is negative 2. So we're going to have a negative from the formula, and we're replacing b with negative 2. So we have negative 2 divided by 2 times a, and a is 1. So as we simplify, we get positive 2 over 2 or positive 1. So the x-coordinate of our vertex is x equals 1. Now, to find the other half of our coordinate pair, we're going to calculate f of negative b over 2a. So the x value that I just found, I'm going to filter right back through the function, and that's going to spit out the corresponding y value. So I'm just plugging 1 into this function by replacing all the x's with 1. Then we can calculate. Looks like we would obtain negative 4. So the ordered pair for our vertex is 1, negative 4. Now let's go ahead and plot that on our coordinate plane. We'll plot our information as we find it. The vertex is right 1 and down 4. So our vertex has ordered pair 1, negative 4. Now remember, the parabola opens up. So if my vertex, as it is in this case, below the x-axis and opens up, then I can anticipate it's going to cross the x-axis twice. So I'm going to anticipate 2 x-intercepts. But before I get those x-intercepts, let's go ahead and find the axis of symmetry because it's convenient at this point in time. Recall that the equation for the axis of symmetry is x equals negative b over 2a. So I can say my axis of symmetry has equation x equals 1. So whatever the x-coordinate of your vertex is, that's the number that you use for the equation for the axis of symmetry. Since this is a vertical line, be sure you write the equation of that vertical line. 1 is not sufficient. 1 is a one-dimensional number, right? Or a point on the x-axis. X equals 1 describes every point along this vertical line that has an x value of 1. So just be careful to quote the axis of symmetry using its equation form. Now, let's go ahead and move on to our y-intercept. The y-intercept is very easy to find. Here's the long way to do it. To find the y-intercept, we set x equal to 0. Let me write that a little more clearly. Set x equal to 0. So on the left side of our function, we have f of x, but we know that's the same thing as y. So I'm going to go ahead and write that as a y. And when I replace all the x's with 0, do you see that the constant is left behind? So again, the shortcut for finding the y-intercept is just to look at this number right here. As an ordered pair, x is 0, y is -3. So we can go ahead and plot that on our coordinate plane. X is 0, y is -3. Now, let me show you how to use the axis of symmetry to construct a nice symmetric parabola. This particular point is 1 unit away from that axis of symmetry, so I can anticipate that there will be its mirror image 1 unit away on the other side of the axis of symmetry. So I'm going to go ahead and put an anchor point over here to help me to construct a good parabola. The last points that we need to find are the x-intercepts. We obtain the x-intercepts by setting y equal to 0. So looking at our original function and replacing this left side with 0, we need to solve. Here's the plan. We need to solve the equation 0 equals x squared minus 2x minus 3. Suddenly, we find ourselves back in Unit 2, solving a one-variable quadratic equation. The options here are factoring, quadratic formula, or completing the square. The square root property would not work on this one. This one's really quite simple to factor. Notice we could factor it as x minus 3 times x plus 1. So we're going to get two solutions from this equation. One comes from each factor. When I set x minus 3 equal to 0 and solve for x, we get x equals 3. And in this case, we get x equals -1. Now, we don't want to put those together as an ordered pair. Each x value belongs to a distinct ordered pair. So when x is 3, y is 0. When x is -1, y is 0. So those are our two x-intercepts. So we can go ahead and plot both of those points on our coordinate plane. Now, as soon as I do that, I'm going to use the guide of my axis of symmetry to double check those x-intercepts. Notice this one is 2 units away on the left. This one is 2 units away on the right. So since they have fallen in symmetric places about that axis, we can be pretty confident that we have the right values. Once we have all of those points discovered and plotted, then we can connect our parabola with a smooth U-shape, and we have correctly constructed the graph. Notice the domain of this parabola is -infinity to infinity, and the range is going to go from -4 to infinity. Again, that -4 is the y value of our lowest point, and infinity is the highest point. Now, the best news about graphing functions is we can always verify with our calculator. So if I go to y equals and type in the original function, x squared minus 2x minus 3, and graph the parabola, we not only will be able to see the shape of our parabola, but we can check the points as well. If I press second and then table, I'm going to be able to verify our points. So notice there's our x-intercept, -1, 0. Our y-intercept, 0, -3. Our vertex, 1, -4. And our other y-intercept, 3, 0. So everything is verified, and we can be confident that that's the correct graph. So this process is very different from graphing by transformation, but it is also very direct. You're calculating those points directly. Let's practice this same process on example B. Remember, the first thing that we want to discover is the orientation of the parabola. To do that, we identify the leading coefficient, which in this case is 2, and observe it is positive. Since it is positive, this parabola is going to open up. Once we have that information, then we can calculate our vertex using the new formula, -b over 2a, f of -b over 2a. I hope you understand, really, you just have to memorize the x value, because once I get that number, I just plug it back into the function and that spits out y. So that's a pretty easy formula to remember. Let's begin by calculating our x value, -b over 2a. From the original equation, we can see that b is -4. So we're going to need the negative from the formula, and we're replacing b with -4, divided by 2 times a. So in the numerator, we have +4. In the denominator, we have 4. So the x value of our vertex then is 1. To find the corresponding y value, we just plug that number 1 back into the function. So we obtain 2 times 1 squared minus 4 times 1 plus 5, or 2 minus 4 plus 5. Looks like we get a value of 3. So the ordered pair for our vertex is x equals 1, y equals 3. Okay, let's keep up with this information on our graph as we go. If x is 1 and y is 3, our vertex ends up over here in quadrant 1. Now, remember, our parabola opens up. That makes this vertex a minimum. If our parabola opens up from here, notice it's never going to cross the x-axis. So I'm going to go ahead and make the observation while we're here that there are no x-intercepts. If you are paying attention, you're going to save yourself a lot of work. If I didn't notice that, and I wanted to solve for the x-intercepts, and I set my function equal to 0 and solved for x, I would end up with imaginary solutions. Okay, so if you do the algebra, you set your function equal to 0, you will end up with imaginary values. If you get imaginary values, that simply means no x-intercepts. Okay, so this would yield imaginary values. Okay, so again, my recommendation is pay attention to the direction of opening in combination with your vertex and use that to anticipate how many x-intercepts you're going to have. That way, if in this case you can see there's no x-intercepts, you don't have to put any effort in to do the algebra to show that. Okay, while we're here on the vertex, let's go ahead and write the equation for our axis of symmetry. Remember, it is x equals whatever the x-coordinate of our vertex is, and in this case, it is x equals 1, same as our last example. So we're going to construct the axis of symmetry as a vertical line, and I will label it as equation, not just 1, but x equals 1. Now, can you look at this function and determine what the y-intercept is? Remember, for the y-intercept, x is always 0, and the shortcut is whatever constant we have out here gives us our y-intercept. So 0, 5 is our y-intercept. Now remember, this parabola will have no x-intercepts, so I only have 2 points to graph this parabola. But again, we can use our axis of symmetry, treating it like a mirror, to anchor the right side of the parabola. So notice this is 1 unit from the axis of symmetry, so its mirror image buddy should be 1 unit on the other side. Once we have that anchor point, then we can smoothly connect our points in a U shape, and we have constructed the graph of the parabola. As always, the domain is -infinity to infinity, and the range goes from our lowest elevation 3 up to infinity. And again, you can certainly verify that with your calculator. So please observe on that one how we did the shortcut. The vertex was above the x-axis and the parabola opened up, so we can anticipate no x-intercepts, so we don't even have to put the effort in to do the algebra. Let's do our next example. Each of these examples is just a little bit different, so I want to make sure you have enough information to handle all the different things that can happen. Notice in this case, our leading coefficient is negative, so that means our parabola is going to open down. Let's go ahead and find our vertex. That's the most important point on the parabola. And we'll use the formula -b over 2a, f of -b over 2a. Starting with the x-coordinate, which is -b over 2a. In this case, b is equal to 4. So we're going to have the negative from the formula, and we replace b with 4. and a is -1. So we have -4 divided by -2, which is +2. To find the corresponding y value, we're going to plug 2 back into the function. So we observe -2 squared plus 4 times 2 minus 4. Now, do be careful on this one. From the original first term, the exponent only works on the x. It does not square the negative. So this means we have the opposite of 2 squared, or -4. -4 plus 8 minus 4. Looks like we end up with 0 for our y value. The vertex then has ordered pair to 0. So I'm going to plot that on my coordinate plane. Vertex is to 0. While we're here, let's go ahead and write the equation for our axis of symmetry. It's always convenient to do it at the same time that you're doing your vertex. Our axis of symmetry is x equal to whatever the x coordinate of our vertex is. In this case, x equals 2. So we have a vertical line passing through the vertex at x equals 2. I'm going to label it with its equation to make it complete. Now, let's consider the combination of our vertex and the orientation. This vertex, notice, is on the x-axis, and this parabola opens down. Well, if this parabola opens down, then it has already encountered its x-intercept. Notice, in this case, the vertex is the x-intercept. So this parabola only has one x-intercept, and it is the vertex. So let's make an observation. There's only one x-intercept, and it is the vertex. We can see that here because y is equal to 0 for our x-intercept. Now, since we only have one x-intercept, that means the parabola is going to bounce at that vertex. Later, when we study polynomials, we're going to see a similar thing happen, and our parabola is bouncing at that x-intercept. That means it's going to touch the x-axis and turn around and go back the other way. The only thing we lack is an easy piece of information, that is the y-intercept. For every y-intercept, x is equal to 0, and let's use our shortcut. The y value of our y-intercept is always that constant. So 0, -4. Again, I only have 2 points at this point to construct a parabola. So I'm going to use my axis of symmetry to anticipate a mirror image point over here. And the point of that, again, is just to help me to draw a nice symmetric parabola. So it bounces at the vertex. Whoops. And opens down. The domain for every parabola is -infinity to infinity. And the range in this case, now remember, when you quote the range, go from the lowest y value to the highest y value. The lowest y value in this case is -infinity, and the highest y value, or its highest elevation here, is 0. So -infinity to 0 is our vertex, is our range. Again, pay attention to how does the vertex fit in with the orientation. You can use that to avoid a little bit of algebra if necessary. By the way, if I wasn't paying attention and I went ahead and found the x-intercepts, what I would end up with would be something like this. If I did all the work, I'm not showing my work here. Anyway, if I did the work and I factored it, I would end up with something like this. I would only get one solution, that is x equals 2, but it would actually count twice. That's called multiplicity, and we will be learning about that in the next unit. Let's do one last example for this. I do want to remind you that even though we're studying this new approach, you still have the ability to use transformations, and this is the perfect example to use transformations to save yourself maybe a little bit of work. Notice this is an ordinary parabola that has been shifted down 3 units. So if we remember our parent function, I'm sure it's fresh on your mind. There's our parent function. y equals x squared, then to obtain the graph of this new function, we just have to shift every point down 3 units. So I'm going to start with the rightmost point and move down 3 units. Then the vertex. Working my way across all of those points. It's a rigid transformation, so it's like looks like I'm picking up the black parabola, moving it down 3 units, and then setting it down. Okay, so here is the graph of our parabola, y equals x squared minus 3. However, we need to identify all of the important points. Clearly, the orientation is that it opens up. The y-intercept is the same as our vertex. The vertex is 0, -3. The y-intercept is 0, -3. The only thing that we don't have specifically here are the x-intercepts. And notice they're not at an exact integer location. So let's talk about how would we find our x-intercepts. We're going to do it as we always do by setting y equal to 0. And remember, f of x is the same thing as y. So I can solve 0 equals x squared minus 3. Now, this is the perfect example of an equation that we could solve quickly and efficiently with our square root property, right? I've isolated x squared. Then I can take the square root of both sides, not forgetting the plus or minus. So we end up with plus or minus square root of 3 equals x. Well, we have irrational x-intercepts. Here's what they look like in exact form. Negative square root of 3, 0, and positive square root of 3, 0. So if I want to label these points, this one would be negative square root of 3, 0, and this one on the right is positive square root of 3, 0. Now that might not make a lot of sense to you unless you recognize square root of 3 is approximately 1.7. So the approximate location is about 1.7, but the exact location is labeled by positive and negative square root of 3, 0. To finish, our domain here is negative infinity to infinity. And the range goes from our lowest y value, -3, to the highest, which is infinity. So this is our new approach to graphing parabolas.